I was trying to pick a new antenna. I wanted a wire antenna that had multiband coverage and good directionality. And I decided to use what they call the Skywire antenna. And I decided to try to learn about some of the design tools that are available to hams when they're evaluating an antenna. So this presentation, I want to share with you some of the things that I learned. You can advance it, Bill. There's the Skywire antenna. This is a common diagram. That's the conventional standard pattern for a loop antenna. It's a square. It's one wavelength long. It's fed with ladder line. And the shape is not necessarily a major factor. You see the slide on the right. Now here's a case where a fellow had to use a rather unusual shape, but it still achieved the same benefits that we wanted to get. He had a power line over there in the upper left-hand corner. I don't know if I can, where's the mouse here? Oh yeah, okay. And he's got a power line up here to deal with. I guess you don't see the mouse on that screen.
Yeah, we do.
Oh, you do? Okay, good. So anyway, he went to a diamond shape. In my particular case, I had 4 trees that were around my house, and it lent itself to a rectangular, one wavelength, 80-meter antenna, 280 feet long. So that's the plan that I was going to use. And what? Oh, okay. So there's the antenna, one wavelength, approximately on 80 meters. We had to advance it now. The antenna wire itself, pretty straightforward, AWG 13, 19 strand, copper clad with polyethylene jacket, brake strength of 400 pounds. The antenna was going to be up 43 feet. That was my intention. Now, here's a simple model of the antenna. It's just a rectangle, 43 feet in the air on easy neck. It's very easy to model. And in this case, if you want to make any changes, make it 5 feet higher, 5 feet lower, or 20 feet longer. It's very easy to do on the screen, and you get your results right away. So it takes some of the guesswork out of it, the trial and error. If we look on 80 meters, this is the radiation pattern, the far field radiation pattern on 80 meters. It's a spherical shape. The rectangular loop antenna is at the very bottom. And as you can see, much of the radiation is going straight up, very little going out to the sides. So on the primary frequency, the 80-meter loop antenna, when you run it on 80 meters, tends to be an NVIS antenna. It sends the signal up straight, and you're very limited in your coverage beyond a couple of 100 miles. In this case, we're looking at the elevation pattern diagram, and I want to call your attention to the fact that the cursor is right at 12 o'clock, and that's the high gain point. It shows as 0 dB. The outer loop gain is 8.17 dB. So going straight up, you have great gain, 8.7 dB. Now I moved the cursor to a more realistic place down here around 30 degrees, and you see that the gain is now 1.35 dBi, so not so good. So we move on to what does it look like on 40 meters? Well, it looks a lot better on the far field radiation pattern. We're starting to get the development of some lobes. And if we look at the azimuthal pattern, you can see that it's putting out a signal in all 4 directions, which is good. It's only about 7 dB of signal strength, which is basically comparable to a dipole. but at least it's getting me the directionality that I wanted, and it's getting me the ability to work on multiple bands. Now, in this case, we're looking at the elevation plot, and you can see where the cursor is, the little green dot there, and that is at 41 degrees. My maximum gain point is 41 degrees. So not particularly useful for DX or anything like that. EasyNet also gives you the SWR, and this plot shows that I was using 370 ohm feed line. So EasyNet calculates the feed point impedance of the antenna, and you tell it the feed point impedance of your feed line, and it works out the SWR for you. And you can see here that it had a pretty good SWR range over the CW portion of 40 meters, which is where I wanted to use it, down below 1.5. The important thing to notice here, I think, is that this graph gives you the feed point impedance of the antenna at this particular height in your particular configuration. And we're going to come back to that because that's a very useful piece of information. EasyNet also gives you the current on the antenna. Now, since we're on 40 meters, that is 2 full wavelengths on this 80-meter antenna. And you can kind of see there's 4 humps. And EasyNet gives you the option of displaying antenna currents either as full sine waves, which would incorporate the direction of the current as well as the magnitude, or making all of the humps positive, so it looks like full wave rectified.
They're only seeing the left one.
Well, that's what I'm still talking about.
Oh,
yeah. So it may seem kind of funny to see all of the currents above the axis, and because that would imply that they're all going in one direction. But really, for the sake of clarity, EasyNet puts it that way, even though the current in alternate lobes is going in different directions. So along the side, the current is going to the right, and then the next lobe, the current is going up. Well, this is the situation on 20 meters. Now, 20 meters really turned out to be pretty good with this antenna. So, because now you're on the 4th harmonic of this thing, so it's, it's starting to work pretty well. And you can see from the azimuthal pattern, the azimuthal pattern on the right, I've got the cursor positioned about 2 o'clock, and it's showing me a gain of 10.7 dBi. And I've got 4 nice lobes. It turns out that the lobe where the cursor is at, if you lay that down on an azimuthal map, that's pointing right through Germany, so that I have a nice wide beam with about 10 dB of gain going to Europe. So that's useful. This shows the elevation plot. You can see that we're down at a more respectable angle of elevation now, about 22 degrees for maximum gain. So that could be useful. The SWR plot shows reasonable SWRs below 3. We can live with that. And now we go to, these are the currents on the antenna. And this is one of the things I found most helpful about this EasyNet program. When it displays the currents, it gives you a chance to actually visualize what's going on on the antenna itself. You realize that each hump, the height of the hump represents the magnitude of the current, and the fact that it's above the axis tells you the current's going in one direction. If we had it displayed so it also went below the axis, you'd know that the current in the next hump is going in the opposite direction. But when they're all above the axis, for clarity like this, just keep in mind that the current in each adjacent hump is going in the opposite direction, 180 degrees. It keeps shifting. Now at 10 meters, it really, all hell breaks loose here. It turns out to be quite a hodgepodge. And of course, what's happening here is that the signal is starting to fragment to the point where we're not getting much energy in any one direction, but we are getting a lot of choices. Pardon me?
It's a lotus flower.
A lotus flower, yeah. But if we look at the azimuthal plot, and I've got the cursor positioned about 2 o'clock again, we see we have about 11 dB of gain. So we didn't really pick up much. We picked up 1 dBi of gain going from 20 meters to 10 meters. And we don't have a particularly wide lobe. We've got about a beam width of 13 degrees before we're down 3 dB on that lobe that's highlighted. But where we really did get some pickup was in our takeoff angle. And now we've got the cursor elevation at 12 degrees, and we've got a 12 dB signal, 12 dBi signal. So that's useful. This opens up some possibilities. But again, the energy's badly fragmented. You've got these lobes all over the place, so you don't get too much energy in any one lobe. And our SWR plot, same deal. That looks fine. We look at the currents on the antenna. Now we're looking at basically the 8th harmonic of the current at 10 meters. You see all those little humps, and you realize that the current in each adjacent hump is going in the opposite direction. And you can see why that sets up all of those constructive and destructive interference patterns that we saw that gives you that real hodgepodge of radiation. So much for the antenna. Now let's talk about the feed line. Loop Skywire antennas have reasonable impedances over the HF frequency range. Now here I'm speaking only of the harmonically related frequencies. If you tried to use this on 17 meters or 15 meters, it might be a different story. But here we're talking about the harmonically related frequencies, 80, 40, 20, and 10. These are the impedances that I took off the charts that EasyNick gave us earlier in the discussion. So 83 ohms, 293, 318, 353, these are impedances we can work with. They're not wildly out of line, and they're not terribly reactive. Now, here's where I did a little of something I wanted to do myself. It turns out that an antenna feed line repeats the impedance every half wavelength. So if I came up with a 126-foot feed line, that would be an electrical half wavelength on 80, 40, 20, and 10 meters, all the bands I wanted to work. So if I select my feed line to be 126, that's one half wavelength on 80, 2 half wavelengths on 40, 4 half wavelengths on 20, and 8 half wavelengths on 10. So a 126-foot feed line will transfer the favorable antenna impedance directly to the transmitter. This can be shown using the transmission line for Windows software included with the ARRL antenna handbook. Now, here's where it would help if I can make a pointer. What was the pointer again? Okay, for my transmission line, we had to back it up. For my transmission line, I have a user-defined transmission line. This is window line, 370 ohms, 126 feet long. You kind of have to read down the chart there and just see the data. The frequency over on the far right, 3.55 megahertz. And now I take the impedance at the load, which in this case is the impedance at the antenna. And I select load versus input. This is load here. And I put in the impedance, 74 0.25 ohms resistance, reactance of minus 33.73. And now what transmission line for Windows is going to do, it's going to calculate the impedance at the end of that feed line back at the transmitter, 126 feet away from the antenna. And you can see by the numbers that just having trouble with this cursor. Okay. You can see what the impedance at the input is 76 ohms minus J33. Well, that's pretty close to the impedance up at the antenna that was 74 minus J33. So it's done its job. It's brought the impedance down to the transmitter. It also tells us the SWR at the transmitter and at the antenna. And the SWR at the antenna, they call SWR at load, is 5.02, and that drops down to 4.87 at the line input. Now, perhaps the most useful thing about this program, in my opinion, was this here. You can plot the voltage and the current on your feed line, and you can plot the resistance and reactance on your feed line. And you can see that graphically. And that really brings to life what's happening here. So the horizontal axis is 126 feet of feed line. The transmitter is at the left at 0 feet. The antenna is at the right at 126 feet. Now, the red trace is the voltage, standing wave. The green trace is the current, standing wave. Now, if we had a longer feed line, those traces would just keep on repeating. Every half wavelength, we'd get that positive hump of the voltage, and we'd get that, also it's positive for the current too, although we're only looking at the negative part of it. So that's a repeating pattern. So if we let's start with the green line at the far left. That represents the current. You see that it's way up at the top of the chart, and it comes down and reaches a minimum point halfway up the feed line, right about 66 feet. The green line is at a minimum, and then the green goes up again to the right side. And we can read the current off the left-hand side. We can see that when the current is at a maximum, it's about 4.5 amps. When it's at a minimum, it's a little below 1 amp. Now, at the same time, the voltage standing wave is starting at its low end, going up to a maximum. This is the red wave, going up to a maximum at the middle of the feed line, and then coming back down again at the end of the feed line. So this is a desirable place to feed the signal into the feed line. We have low voltage and high current, which transfers into low impedance. So we aren't trying to match some real wacky impedance. We've got an impedance that's not going to be too far off from the 50 ohms that our transmitter wants to see. Now, I've also programmed in here to run this thing at 1500 watts. You can put in any voltage. If you're worried that you can't, your feed lines won't support a high voltage, you could make that any voltage, and it will scale the graphs accordingly. So you'll know your point of maximum current and maximum voltage. You see up at the top, it gives us the SWR. It's telling us that the load is 74 minus J33 for an SWR of 5. Now, if we were to take the peak of the red wave, the voltage, and divide it by the minimum point on the red wave, that would be the minimum voltage. We'd have maximum voltage divided by minimum voltage. It would come out to be 5. It would equal the SWR. The same thing on the current. If we take the green line which is axis on the right. I'm sorry, the green line is axis on the left. And we take that reading, about 5 amps, and we divide it by roughly 1 amp minimum, and that equals the SWR. So the voltage and current SWRs are going to come out the same. But what's really interesting about this diagram is the relationship between the standing waves. Now, these standing waves are constant. They're a quarter wavelength apart, their peaks, and they repeat all along the feed line. Now, since our feed line is only half a wavelength long, is 126 feet, that's half a wavelength on 80 meters, we're only looking at one cycle of the standing wave. And I use the term cycle a little differently than we ordinarily think of it. We think of it as a full sine wave cycle. I'm just talking about the wave starting at its minimum value, going up to its maximum, and coming back down to its minimum. So the red wave starts on the left-hand side of the screen, it goes up to the maximum in the middle of the screen, it comes down on the right-hand side of the screen. That's what I'm going to call a cycle. Now, if you look at the green waveform, the green waveform is coming down. It's ending its cycle. We can't see the full cycle because it's off to the left and our feed line isn't that long, but it would look just like, the red wave. It would have a basically same shape. So the green line is coming down, finishing its cycle. The voltage is just starting its cycle up. So that tells us that the voltage waveform is lagging the current waveform. The current is finishing up at the same time the voltage is going up. So we know that current leads voltage in this part of the feed line. And that happens to be the characteristic of a capacitor. We pump charge into a capacitor, we build up the current, and the voltage begins to go up. It's a lagging function. So the left half of the feed line from 60 feet back to 0 is acting as a capacitor. Now the right half of the feed line, the story reverses. The voltage waveform, which is the red waveform, is on its way down. It's finishing its cycle. The green current waveform is on its way up. It's just beginning its cycle. So in this case, the voltage is leading the current. And voltage leads current with an inductor. You put the voltage across the inductor, and eventually a current materializes within the inductor. So we have the feed line acting capacitively on the left side and inductively on the right. And believe it or not, there is a brief period of time when the feed line acts as a resistor. And that is when the waveforms are at the point where they have 0 slope. So the voltage waveform is at the very top, that very instant when the slope is 0, and the current waveform is at its minimum. At the same time, that slope is equal to 0. Both slopes are equal. That allows us to say that the waveform, just for that brief instant, the waveforms are in phase. Now, when current and voltage are in phase, that's characteristic of a resistor. So the middle portion, the feed line acts as a resistor at 66 feet. The first 60 feet, it's acting as a capacitor, and the last 60 feet, it's acting as an inductor. So what does all this mean? Well, the other plot that we can get from this Windows program, transmission line for Windows, is an impedance plot. Now, on the left-hand side, we have the reactance, and on the right-hand vertical axis, we have the resistance. So look where the green line starts. The reactance line is starting right around 0 ohms. what a perfect place to feed a feed line. We don't have to deal with a lot of reactants. We're going to feed a resistive load, basically. Now, if we advance a little further to the right, up maybe 25 feet into the feed line, we see that it's getting more capacitive. The green line is going down, and you keep in mind that the zero reactance point is right in the middle of the graph horizontally. So when we're above that middle of the graph, we're inductive reactants. When we're below it, we're capacitive reactants. So we go down to about 600 ohms capacitive. We're ignoring the red wave for a minute. And then look what happens to the green wave. It shoots all the way up from maximum capacitive reactance to maximum inductive reactance. Just bang, like that. And in order to get there, it had to go through a period of zero reactance. And that is that brief instant we talked about where the slopes of the current and voltage standing waves are equal. It just stays there for a second, and then it goes to maximum inductive reactance, and then it starts leveling off. The voltage, on the other hand, at the introduction point of the feed line way on the far left, the red trace is at a minimum voltage, and that's what we want. We want to feed at as low a voltage as we can. And then about the middle of the feed line, the voltage goes up higher, and then it comes down as we move further to the right. Any questions or comments on that? Because that's a lot of stuff. And if I can make it any clearer, I'd like to do it. I wish I could use the pointer better, but I think the description, as long as you're seeing it in color, the description should work okay. Any feedback, comments? Okay, let's move on to the situation at 40 meters. I'm not going to go into all the detail here. It's the same idea. The transmission line for Windows screen allows us to put in the impedance at the antenna, which it calls the load impedance. In this case, we're putting in 291 ohms and a reactance of plus 20.27 ohms. We're specifying that that is the load reactance, and the program generates for us the reactance at the input of the line. And you can see the very bottom line on the chart. The input impedance is 292 plus J20. So same thing. The half-wave feed line has transferred the impedance from the antenna right down to where we want it, right at our receiver. The same waveforms here, we don't need to discuss them. The red is the standing wave of voltage. You can see how it repeats. It just repeats all along the feed line. Every half wavelength it repeats. The green is the current that is 90 degrees out of phase with the voltage, and it repeats down the feed line. So I guess I don't have to say much about this. We've talked about that. If we go and look at the impedances, the reactance chart, again, reactance is on the left, resistance is on the right. It's giving you both components of the impedance on the feed line, and it's showing you that we're coming in at a pretty good point. We're up to about 20, maybe 30 ohms on the green as it starts its trip down on the left-hand side, 30 ohms, and we're down at a minimum voltage. The voltage is, I'm sorry, I'm getting mixed up here. We're down at a minimum resistance. The resistance is red on the right-hand scale, and it's the red trace, and it's about 300 volts. So again, we're feeding at a point of low reactance and relatively low voltage. And that's where we want to feed it. Now, where do we go from here? We've brought all these relatively good impedances down to the transmitter, but could we make it a little better if we put a 4-to-1 balun on there? And this is actually up for grabs. You get some improvement with a 4-to-1 Ballon, you get some improvement with a 1-to-1 Ballon. And it's almost a trade-off. DX Engineering recommended the 4-to-1, so that's what I went with. So if we look at the middle of the sheet, the impedance of 83 ohms coming into the top half of the Ballon, the 200 ohm part, is 83 ohms. You divide that by 4, you're getting 20.9 ohms on the low side, the 50 ohm side of the Ballon. So that gives us impedance of 20, 73, 79, and 82. So what are those VSWRs? Because we're coming on a 50 ohm coax line. And here I was a little handicapped because I didn't have an antenna analyzer at the time I put this antenna up. I would have liked to measure the actual impedance on the low side of the Ballon, but I didn't have that, so I had to go with the calculations of taking the high side impedance and dividing it by 4. So I'm assuming I have 20, 73, 79, and 88 ohms. I'm mating that up against a coaxial 50 ohm LMR 400 cable coming out of the bottom of the Ballon and into the shack. That gives me a VSRs 1.7, 1.4, 1.5, 1.7. So not too bad of VSRs. What we're trying to do here was make the job of the tuner as easy as possible. So if we can give the tuner something that's already relatively close to 50 ohms, it doesn't have a lot of reactance, the tuner's going to be happy. So I did have to deal with this 25-foot run of coax, which goes from the Ballon into the ICOM transceiver. And that would change the impedance, but since I wasn't able to measure the impedance directly on the low side of the Ballon, I didn't really worry about what this 25 feet would do, but it would have a slight impact. So when I actually got in and connected it up to the tuner, now this is an ICOM 7610 running 100 watts and using just the tuner in the ICOM transceiver. You can see that I got these very low SWRs. Really, you might say ridiculously low. I mean, it is not necessarily necessary to go to these extremes. This was just part of my experiment. Any reasonable tuner, if it's properly tuned and if it has low loss line, should be able to handle this with almost any length of feed line. But I wanted to see what it would be like if I made the optimum feed line. So you see, I got very little reflected power there. So these are excellent VSWR readings, and any reflected power can be returned to the antenna by using low loss window line and coax line. And that would be the case. So here is the DX Engineering Ballon, 200 to 50 ohms, rated high power, 10 kilowatts continuous. I put it in a box, and I have my ladder line coming off the top, and I have my coaxial LMR 400 coming off the bottom into the shack. I put this little insulation in there, not because I had high voltage on the feed line, but because I didn't want the metal case of the Ballon to interfere with the signals on the ladder line. And I ran it up and out the little hole there for a drip line. Now there it is, it's up on a post. And the coax is coming out the bottom, kind of hard to see it in this slide. And the ladder line is basically going straight up, goes up 43 feet. Now, if we look at the feed line, I've got the antenna up 43 feet, but I've got a 126-foot feed line. So what am I going to do with all this extra wire? Well, I had to make a clothesline type of thing. And you can see it there with those two posts, the ladder line going back and forth. And you have to twist the ladder line so that the adjacent rows won't interfere with each other and stuff like that. But that all worked out fine. You go into the shack, it's, well, there's really nothing to see here except the shack. So final thoughts. I can't really say that my approach was any better than running a convenient length of ladder line to a balanced external tuner in the shack. In fact, considering the time and costs of putting in the posts, I probably lost money. It's just something that I wanted to do to learn more about antennas and feed lines. That's the part of the hobby that I enjoy the most. So that it is. Any comments, questions? We can go from there.